Hi, everyone. First, thanks, Dr. Graham and Taylor's great presentation. It's also my great honor to present my work here. My name is Ely. I'm from the Baidu Silicon Valley AI Lab. Today, I'm going to present my work of cancer metastasis detection with a new deep learning algorithm we proposed called neuron conditional random field. So just a bit background on this topic. To the best of my knowledge, among most of the medical diagnoses, a pathologist slides review from a pathologist is often considered as the gold standard, especially for diagnosing a cancer. But finding the tumor cells, especially any of those tiny but clinically actionable tumor cells within a glass of pathology slides can be potentially difficult. For example, a typical digitalized pathology slide at 40x microscope is literally taking up 1 gigabyte or even more disk spaces and are composed of billions of pixels. And this is just an overview of the slides. If you're asking me to find any signs of tumor cells here, I just cannot find it. What you have to do is to have to zoom or even zoom in again to these very fine details. Then you probably can tell, okay, this is the parts of tumor cells as compared to the surrounding normal cells. But with respect to the global picture here, you probably have to do this zooming process to go into these fine details for every potential locations, which can be very difficult and time-consuming. So a natural question arises from this is, can we use computational algorithm or even just deep learning algorithm to help to ease this process? The short answer to this question is yes, there are actually lots of methods have been proposed to tackle this problem using deep learning algorithm. And most of these algorithms are using this, what I call patch-based classification algorithm. What they do is that they split these giant pathology slides into lots of these image patches like here, and typically 256 by 256 pixels. And then they go through our off-the-shelf standard convolution neural nets like VGG or more recently ResNet to classify each of these patches is normal cells or tumor cells like this. And there are lots of methods in this category, and including the one who won the Chameleon 16 Challenger from Harvard MIT. But in my opinion, I think there's a fundamental difficulty in this kind of methods that are just, if you're just looking at one 256 by 256 patches like this one. If you're asking me as a non-expert in pathologies, if this is tumor cells or normal cells, I probably will guess this is actually tumor cells. But if you zoom out a little bit to look at the context, the surroundings of these patches, your idea may be changed. Actually, I look at the annotations from the pathologists. This is one of our examples of hard negatives. But the point I want to make here is that sometimes, especially around the boundary between tumor and normal regions like this, you probably need to zoom out a little bit, like probably pathologists would do to look at the context of the region you're interested. Then you can make more confident calls. So that's drive us propose this model, which I call neuron conditional random field or NCRF. The way our algorithm handles these tumor slides is that rather than taking one image patch as input, we take a grid, typically 3 by 3 patches of input. And then we're going through this CNN architecture to extract the feature embedding or a vector representation for each of these patches within the grid. And after that, we use a fully connected conditional random field, or fully CRF, to model the spatial correlation between the patches within this grid and jointly predict, okay, each one of them, are they tumor or normal? So actually, we're not the first to propose the idea of taking a grid of patches as input to consider spatial correlations. To the best of my knowledge, there are already 2 work on this track. But both of these 2 work, they use this, I call it a 2-stage training. What I mean is that during the first stage, they again still take each independent patches to extract the feature embedding from a typical convolution nets. Then in the second stage, they do an offline post-processing to consider the spatial correlation, either through a 2D LSTM or through a conditional random field. Our method is that we're just directly incorporating this fully CRF on top of the CNN feature classifier. So the good way of doing this is that we can now train the whole algorithm end-to-end with a standard backprop. And because now the convolution neural nets are aware of the spatial correlations between patches through the CRF, it actually improves the classifier of the CNN feature extractors as well. And because I offload all the computations, including CRF1, onto GPU and train end-to-end, it pretty much introduces very minor computation overhead, like less than 0.1 seconds per mini batch. So that's the overview of our proposed algorithm. Let's see a little bit details of each component. So for the CNN module, it's pretty much the standard ResNet, not too much to say. We tried ResNet 18 and the ResNet 34 in the paper. For the CRF module, we derive in the following the standard convention. We use the negative energy. We use the unary potentials and the pairwise potential to denote their energies. For the unary potential, it's just the negative logis out of the CNN classifier. For the pairwise logis, we design it as the cosine distance. It's a number between 0 and 1 to measure how far away based on the embeddings from two patch embeddings. And finally, we use the standard mean field approximation to do the inference. And this is actually a snapshot of the code for this algorithm. This is literally just a copy-paste from the PyTorch release for the ResNet, except a minor difference here, if you are going to use the CRF module or not. And it's pretty handy. And the CRF module here only have one trainable parameter, which is this coefficient weights that are measuring the relative correlations between the patches within the grids. And if it is 3x3 patches, 3x3 grids, which is 9 patches within the graph, then this is just literally 87 floating point numbers to train. And actually, if the model is training well, converges well, sorry. Okay, cool. So if the model trains well, if you plot the weights, it actually show you a very nice shaped spatial features over there. So this figure is a little bit technically involved. I don't have time to go to the details, but relatively speaking, each subfigure here represents one patches within the grids. And what you can see is that for most of the patches, or actually all of the patches, it's always the closest neighboring patches have the largest impact on the one there you are interested in. So that's the model. Let's see the results. So here are the standard experimental setup. I'm using the Chameleon 16 data set. I'm not going to read through the details of all this. It's pretty standard way for data augmentations and other stuff. But there's a little bit minor details I'd like to point out is that we just use a fixed learning rate to train 20 epochs. We don't schedule the learning rate. And during the inference time, we use an inference stride of 64. And we only use a single direction prediction for each patch when we obtaining the probability map. For each of these parts, you can probably improve by scheduling the learning rate, making much smaller inference stride, or using 8 directions, the average, to obtain the probability map. But I just don't have enough time to finish that part. Okay, let's take a look at the results. First, I mentioned that because the CNN feature classifier are directly connected to CRF, so it benefits by knowing the spatial distance between the neighboring patches. What I show here is the patch classification accuracy on the training set of our model, NCRF, compared to the baseline model that doesn't use the spatial correlations with 5 different randomseeds. What we can see here is that the patch classification accuracy of our methods, NCRF, are consistently achieving a better accuracy compared to the baseline methods across different randomseeds. And if you look at the accuracy on the validation sets, again, our method is doing better than the baseline for both ResNet 18 and the ResNet 34. We can also look at the probability map obtained through our methods and the baseline methods. Here is an example of test 26. And this is the raw overview from the pathology slides. This is the annotation from the pathology. And the first figure here is the heat map, the probability map obtained through baseline methods. We can see that for sure it covers the ground truth regions pretty well, but it also introduced quite a bit false positives here. By introducing the hard negative examples, it indeed effectively removes most of these false positives. But if you look at the ground truth regions, the probability density is also reduced, and it's also for these parts. But if you look at our figure here, this probability map obtained through NCRF, we kind of obtain the good sides of both. That is, we both remove these false positive regions, but also while almost retain the probability density around the ground truth regions. Actually, for this specific example, our method here, NCRF plus hard negative examples, detect just two more regions compared to the baseline plus hard negative regions. And in terms of numeric scores, if you look at the average Frog score, for the baseline it's about 0.72. For baseline plus hard negative examples, it's indeed improved quite a bit. It goes to 0.78. But if you look at our examples, our cases, it further goes to 0.7, almost 0.81 there. And we can also look at the Frog score plot on the test set of our algorithm compared to the baseline methods on both ResNet 18 and the 34. So that the solid lines, the NCRF methods, the dashed lines, the baseline methods. We can see that this NCRF methods is consistently achieving a higher sensitivity compared to the baseline methods. And just for comparison, I just screenshot the figure from the Chameleon-16 website. This is the champion of the Chameleon-16 challenge from the Harvard and MIT team. So we can show that after maybe say one average false positive per slice, our methods are consistently achieving a higher sensitivity than this one. And when you go to 7 or 8 false positive per slice, we're achieving a sensitivity more than 90% here. And again, if you run this model 5 different times with different randomsies, we still achieve a consistently better Frog score of our methods than the baseline. So, of course, I know our Frog score is not the best. It's still away from, little bit away from the Google one. So to make up for that, we open source our code, and you are definitely welcome to try that out. It already got like 206 stars and 2 issues already there, and I'm trying my best to document every detail I did during the experiments and trying my best to fix all the issues there. So next steps. First, I was very glad to be told that there are actually 1,000 more slides of colon cancer in Beijing, not here, not in US. So I'm going back to the headquarters at the end of this month to try my algorithm on the new data set. Hopefully we can still maintain this high Frog score there. And for Frog score improvement, I think there are minor tricks to further boost the Frog score, like we can use much smaller inference rate, model ensemble, schedule learning rate, and using different ways to obtain the probability map. But I think in terms of architecture advancement, there are more interesting stuff I'm going to try next. So the first thing I think is to increase the receptive field for this specific problem. I think for NCRF, the equivalent effective receptive field is about 256 multiplied by 3, which is 768 pixels. I think we can go larger, maybe 256 multiplied by 10. And I think probably dilated convolution can be pretty useful in this case. And another point I want to point out is that just enlarge the receptive field probably is not enough. I also want to make a denser prediction. Right now, we are making a prediction for every 256 by 256 pixels. I think we can make a prediction for maybe every 32 pixels, or even at the tumor cells. But I haven't calculated how many pixels for each tumor cells. And I think in this case, fully convolution can be also helpful, just like the work proposed by recently the ScanNet. But I also want to note that for ScanNet, even they use fully convolution during the inference time for a very large receptive field, during their training time, I think they're still using less than 256 pixels as receptive fields. I think that can be improved. So to conclude, I want to go from this figure to this figure. Larger receptive field and denser predictions. And thank you. And I really like to appreciate the organizer of MIDL conference to give me the first spot on the first day to present my work. I also appreciate Radboud UMC and also UMC Utrecht for provide me the download link for doing this work. Thanks so much.
Okay, thank you very much. I'm finishing just on time. Any questions?
Yes.
Just a clarification question. So I take it you do end-to-end learning and you backpropagate through the mean field equations?
Yes, exactly.
So do you unroll them and then have t steps of them and then backpropagate?
Yeah, t-test. Usually I do 10 iterations of mean field in the code.
Okay, and you backpropagate through the...
Yes, that's right.
Thank you.
Yeah.
Any other questions? So maybe I can ask a quick question about this sort of philosophy of using context. There have been some other methods around that as well, what is becoming known as the context-aware networks. I don't know if you've looked at any of those. And there are strategies about using multiple resolutions data. I don't know if you've...
I haven't tried that, but I read from the Google's paper, they say by using multiple resolutions, it seems to improve the smoothness of the probability map as well. I haven't tried that yet. It'd be interesting to look into that.
Okay. If there aren't any other questions, you can thank the speaker again and move on to the next talk.